double integrals over rectangles. So before we look at a double integral and what it means and how to calculate it, we're going to review a single integral that you did in Calc 1. Calc 1, you would integrate from a to b some function in terms of x dx. And that integral told you the area under the curve from x equals a to x equals b. So you would have some curve f of x. You would choose x equals some value a and x equals some value b. That integral then would calculate all of this area. Now, do you remember how you approximated this area before using an integral? You would use the rectangles, the Riemann sums. So another thing to remind you is that the integral from a to b of f of x dx is the limit as n goes to infinity, the sum from k equals 1 to n, f of x of k star delta x of k. This is the area of a rectangle. That's the base of the rectangle. This is the height. Do you remember what that star means?
We didn't have a star.
You've seen it before. Do you remember the idea that when you have your rectangles, as soon as the rectangles get really, really small, it doesn't matter the point you choose in the rectangle to be the height? No? None of this sounds familiar to you? Okay, well, I'm telling you now. So when you guys started with the rectangles, sometimes you use the left endpoint, sometimes you use the right endpoint, sometimes you use the midpoint. We talked about you probably talked about your estimate is going to get more accurate the thinner your rectangles are. Okay, so the idea with the Riemann sum, which this is a Riemann sum, is that you can choose any x within that rectangle. Doesn't matter if it's the left endpoint, the right endpoint, the midpoint. That's what a Riemann sum. That's the idea with a Riemann sum. Okay, so here's what's new then. Calc 3, instead of calculating area, we are going to calculate volume. Okay, so here's the volume problem that we are interested in. Given a function of two variables, that is continuous and non-negative on a region R in the xy plane, we are interested in finding the volume of the solid that is enclosed between the surface z equals f of xy and the xy plane. Okay, so drawing ourselves a picture here. This is what I'm saying. We have some curve that's a function of two variables. I'm going to draw a plane just because that's the easiest one to draw. And then we have some region R that's in the xy plane. What I want to know, bless you, is what is the area between R and our surface, only within the confines of R. So we're not the area, what's the volume? Only within the boundaries of R. So mapping R up to the figure, what is the volume in between the xy plane and the figure? Does that make sense? Okay, so here's the idea then. Here's how we would go about calculating that. First, we're going to partition R into rectangles. Ideally, they would be smaller than that, but I need them a little bit bigger for the figure. Then we are going to choose some point, which I'm going to call x of k star, y of k star, in each rectangle. Again, the star means it doesn't matter which point I choose. So maybe I'm going to choose this point right here. That's my x of k star, y of k star. And then what I'm going to do is I'm going to map that point onto my surface Z. Maybe it's right there. And then what I'm going to do is I'm going to form a parallelepiped. You all know what that means? Okay, anyone review what is a parallelepiped? Oh. Yeah, it's like a rectangular prism. Yeah. I was going to draw it for you, but I'm not feeling that, so we're just going to look at a figure. Sound good? Okay, so here's the idea. Here's your surface. You pick a point, you map it up, and then you form this little rectangular prism. But you would do it for all the rectangles. Do we see how that can be used to approximate the volume? Okay, glad you all are so excited for this. Okay, so then the volume is approximately equal to the area of the rectangle, or the parallelogram, whichever one we have, multiplied by the height of each parallelepiped. And then, of course, we would add them all together. So what that gives us is that the volume is approximately equal to the area. The height is f of x of k star, y of k star. Okay, your book uses slightly different notation. Are you going to be upset that I use different notation than your book? Yeah, it's going to upset us? Okay, but obviously you'll get over it, or you won't, because those are your two options. Okay, so then what this gives us is that volume is going to be more accurate the smaller we make those rectangles. So the volume is equal to the limit as n approaches infinity, the sum from k equals 1 to n, of f of x of k star, y of k star, delta a sub k. So this is the formal definition for that volume problem, the formal solution. This is a Riemann sum for volume. Okay, one thing to know, if f has both positive and negative values, then the volume is the difference in volumes between R and then the parts of the surface below and above the xy plane. So any part of the surface that's above the xy plane is going to have positive volume. Any surface below the xy plane is going to have negative volume. So then when you find the volume, it's going to be the difference between those two, similar to when you did area. Okay, so that is leading us to a definition or a theorem. If f of xy is greater than or equal to 0, then the volume of the solid that lies above the rectangle R and below the surface z equals f of xy is the following. So first is that Riemann sum that we wrote before. Okay, what that is equal to is the double integral over the region R of f of xy dA. So obviously it's not very practical to split the figure up into rectangles all the time. So first we're going to look at an example of how to do it the rectangle way, and then we'll talk about how do you actually calculate a double integral. So what this is telling you is a double integral is used to find the volume below the surface, between the surface and the xy plane. Okay, with me so far? Questions? Here's our first example. We are going to estimate the volume of the solid. That lies above the square, which is 0,2 by 0,2, and below z equals 16 minus x squared minus 2y squared. We are going to divide R into 4 equal squares. And I'm telling us specifically to choose the sample point to be the upper right corner. Of each square. So obviously we're going to get different answers if we choose different points. So I'm telling everyone we have to choose the upper right corner. Okay, so here's what this notation means. These first two are the values of x, second two are the values of y. In this case it doesn't matter, but if we change the values of x and y, if it wasn't a square, it would matter. So this is what we're looking at for R. X is between 0 and 2, y is between 0 and 2. We're going to divide it up into 4 equal squares. So this square is r of 1, 1. This one is r of 1, 2. This is r of 2, 1. And this is r of 2, 2. Okay, now the volume that we're actually finding this is our R. Do we know or do we remember what this surface is? What it's going to look like? We already forgot. Hasn't been that long, guys. We should know what that looks like. You got nothing? When you keep plugging in values for z, what will your traces be? Ellipses. Yes, it's an elliptic paraboloid. Oh, that was kind of torturous. Elliptic paraboloid. So z is going to come up here. It's going to come down something like this. So we are specifically interested in the volume between our surface and this square. So mapping our square up onto the surface. Okay, so if we wanted the actual volume, it would be the double integral over the region R of our surface, which is 16 minus x squared minus 2y squared dA. We're not actually going to calculate that, though, because we don't know how to yet. That is going to be approximately equal to the volume of the 4 parallel pipets. Okay, volume of each parallel pipet is going to be the area of the base times the height. Area of each base square is 1. So it's going to be 1 times the height for the first one plus 1 times the height for the second one. We are choosing the upper right corner as our sample point. So these points right here. So the height for this parallel pipet is going to be f of 1, 1. The height for this parallel pipet will be f of 1, 2, f of 2, 1, and f of 2, 2. Now we would plug 1, 1, 1, 2, 2, 1, and 2, 2 into our surface to get all the heights, multiply them all by 1, add them all up. Are you okay if I already did that and I just tell you what it is? Okay. So we're going to estimate the volume to be 34. Okay, questions on that? Okay, if you are interested in the figure, here's what the figure looked like. So those are those 4 parallel pipets. You should be able to tell from here, is our estimate going to be an over or underestimate? Underestimate, right? And we're only going to be able to tell by looking at the figure. Okay. Sound good? We're not going to write down this rule. I'm just going to verbally tell you it right now. The book, for some reason, has a special rule called the midpoint rule. Midpoint rule just means use the midpoint, like the center of each square. Sound good? Okay, great. We're going to do one more example, and then we'll talk about how to actually calculate the double integrals without using an estimate. Okay, if R is the following, so this is another notation that you might see. It might not always be R. I think your book sometimes uses D, sometimes it uses E, so it might be a different letter each time. So this is saying the rectangle is when R is between -1 and 1, or when X is between -1 and 1, Y is between -2 and 2. We need to find the volume of this surface. Okay. This tells us that Z is the surface square root of 1 minus x squared. What is that surface? Half of a cylinder. Half of a cylinder. If you square everything, you get z squared equals 1 minus x squared. So then x squared plus z squared equals 1, except that z is only the positive half. Okay, so if we draw ourselves a picture, x is only between -1 and +1. Y is between +2 and -2. have the cylinder that we're trying to find the volume of. Okay, in this case, we don't need the rectangles. We don't need to split up R. We know how to find the volume of a cylinder already. Well, we should at least. Volume of a cylinder? Pi r squared h, except that we only have half of it, so we're going to do 1/2 pi r squared h. What is our radius in this case? 1. Height is 4. So we end up with an answer of 2 pi. So this example was to show you that you should use geometry when you can. Sometimes you don't need to estimate, sometimes you can just use geometric formulas. Okay. Do we get the idea of what a double integral represents? Yes? Okay, so now we are going to talk about how you actually evaluate or calculate double integrals. If you are evaluating a double integral, you are going to use what is called iterated integration. Okay, here's how it's going to look most of the time. You're going to have your function in terms of x and y, and you will then be told how to integrate. You will have 2 sets of bounds. Here's how you're going to calculate this then. What you are first going to do is you are going to integrate the inner integral. So that's a to b of f of xy dx. So you're going to integrate with respect to x. Whatever you get, you then integrate with respect to y. It could be the other way around. So it also could be dy dx. So you're starting inside and then going out. So dx first and then dy. Okay, so here's the example that we are going to do together. Okay, so this integral would be used to calculate the volume underneath the surface x squared y between the xy plane when x is between 1, when y is between 1 and 2 and x is between 0 and 3. We're not going to look at the figure, we're just going to calculate. Okay, so again, you're going to ignore the outer bounds for a minute and just look at that inner integral. So we are integrating with respect to y first, which means we are treating x like it's a constant. If I integrate with respect to y, I get 1/2 x squared y squared. I'm then going to evaluate from y equals 1 to y equals 2, and then integrate with respect to x. Sorry. I highly suggest that you write y equals here, so that you remember that you're plugging in for y and not for x. Okay, so then if we plug in y equals 2 and y equals 1, we get 1/2 x squared times 4 minus 1/2 x squared times 1. This gives us 3/2 x squared dx. And then you're just integrating like normal. So this is 1/2 x cubed from 0 to 3. And we get a final answer of 27/2. We're going to do the same one again, but we're going to integrate with respect to x first and see what happens. Okay, so again, we're going to ignore the outer integral and perform the inner integral first. This ends up being 1/3 x cubed y, evaluating from x equals 0 to x equals 3. I plug in x equals 3, I get 9y. And you get an answer finally of 27/2. Same answer. Okay, do we get the gist of how to calculate these? Yeah. Okay. This is not always going to be the case. So you can't just like willy-nilly flip x and y whenever you want. This next theorem will tell us when you're allowed to, but please know, after this section, most of the time you won't be allowed to do that anymore. Okay, so the theorem that's going to tell us when we can just flip x and y is called Fubini's theorem. Theorem says, let R be a rectangular region defined by x is between a and b, y is between c and d, if f is continuous on this rectangle. Then the following. Double integral over the region R of f of xy dA is going to be equal to double integral from c to d, a to b, f of xy dx dy, which is the same as when you flip x and y. Okay. So what's really important here, two pieces. One has to be a rectangular region. So the region in your xy plane has to be rectangular. F also has to be continuous on that rectangle. Okay, next example. We are going to find the volume of the solid. That is bounded above by f of xy equals y sine of xy, and below by r equals 1, 2, 0 pi. So let's set up our volume. It's going to be the double integral of that f of xy, so y sine of xy. R is rectangular, so by Fubini's theorem, it doesn't matter if we integrate with respect to x or y first. So let's do x and then y. X is between 1 and 2, y is between 0 and pi. That's one possible setup. Or we could have integrated with respect to y first. Either one is going to give us the same answer. Okay, do we have an inclination as to which one we should do first, or which one we should go with? Like I said, they're both going to give us the same answer. Sometimes either way will be the same level of difficulty. Sometimes one way will be easier than another. Let's look here. If we integrate with respect to y first, can we do that? Do we know how to? Yeah, integration by parts. Do we want to do integration by parts? No, so don't do this way. Okay, don't do that way. It takes way too much work. So let's do this way instead. And by let's do this, I mean you all do this. So take 2 or 3 minutes. See if you can figure this one out. Can you turn to the person next to you and see where that person is at? Okay. Are we ready? What did we get?
0.
I also got 0. Yeah. So here's my work. Some of you, I saw you guys looking around when you got 0. Why would a volume equal 0?
Equal area above and below the xy
Right.
plane.
Yeah, part of the surface is above the xy plane, part of the surface is below, so the areas cancel each other out. Okay. Hey guys, can we come back together? Can we keep going? Because there is more. Great. Next thing we need to talk about is some properties of these double integrals. First property, if you have a double integral over the region R and you have some constant multiplied by f of xy, you can pull that constant out. So that's going to be helpful. Another property, let's say that you have the sum or the difference of two functions. You then can split that up into two integrals. Another property, sometimes it might be helpful to partition R into two separate rectangles or two separate regions, in which case then you would have two double integrals. And you are going to use that. Now, of course, R1 and R2 have to make up R. Okay. And then lastly, bless you, if you are integrating a function of x times a function of y, you are able to split that up into two single integrals. This last one, I will tell you, is very helpful and very powerful. We're going to use that one a lot. So of course you don't have to split it up, but it's going to make your life a little bit easier. For example, this next one. We are going to evaluate double integral over the region R, sine of x, cosine of y, dA, where R is the following: 0, comma pi over 2, and 0, pi. So that double integral then, doesn't matter the order that I integrate. So let's say I want to do x first and then y. X I'm integrating from 0 to pi over 2. Y I'm integrating from 0 to pi. In this case, it's not easier one way or another in terms of the order of integration. But what you should notice is you have a function of x and a function of y. So what you can do is split this up. I can integrate that sine of x, and x is that 0 to pi over 2. I can integrate that y, and then I can multiply my results. Now, this only holds true with two conditions: function of x and y, and it has to be a rectangular region. So the next day that we take notes, which will be next week, we're going to look at non-rectangular regions. This won't work then. Only works for rectangular regions. I trust that you guys can calculate those, so we're not actually going to do that. Is that okay? Great. Last thing that we need to talk about is average value. So let's say that you're looking for the average value of f or z over some region R. The average value of f is going to be 1 over the area of the region R times the double integral over R of f of xy dA. So that should be similar to what you guys did last year. So last example, we are going to find the average value of f, which is equal to x squared y over the region R that has vertices -1, 0, -1, 5, 1, 5, and 1, 0. So I'm going to sketch us out this region R. So average value then, 1 over the area of R, in this case a rectangle, so 2 times 5. And then we have f of xy, so x squared y. I'm going to integrate with respect to y first and then x. Our y goes from 0 to 5. Our x goes from -1 to 1. We're not going to finish the problem, I just wanted to talk about setting it up. This is another one where you could split this into 2 integrals. How do we feel about double